So hi, we're in the middle of doing a problem, and this problem is number 21 from your homework. And in number 21, they ask you first to find the velocity, and so we simplified S of t a little bit and found the velocity using product rule, and then simplified that. So our velocity is here. Then they ask us to find the acceleration, and that's easy enough. Then they ask us to find the times when the particle is at rest, and that rest means that the velocity is 0. So we express that concept first, and then we have to solve by factoring. Factoring is your friend. And then in part B, they ask us to describe the motion of the particle. To describe the motion, we're going to use our 3 words. Left, right, and stop, or forward, backward, and stop. We're going to do that by taking a look at the sign of the velocity for times in the domain. Now here, our domain is for all t's greater than 0, and so we're going to begin by drawing for ourselves a well-labeled number line, labeled as with velocity or S prime. And then on that well-labeled number line, we're going to put the 2 zeros that we found here, 2 and 10 over 3, which is 3 1/3, like that. And those are the places where the velocity is 0. And now we're going to identify the intervals for which the velocity is positive or negative. And we do that by picking any value that is between 0 and 2 and plugging it into the velocity. Give me a value between 0 and 2. 1. And so I evaluate S prime of 1, and I can evaluate it in the factored form, or I can evaluate it in the unfactored form, either one. I like the factored form because I can easily see this factor would be negative, that factor would also be negative, so the overall is positive. Now I need a value of t between 2 and 10/3. 3. Positive factor here, negative factor there, negative velocity. And finally, I need a value bigger than 10/3, a bazillion. A bazillion minus 2 is positive, 3 bazillion minus 10 is positive, and so we have positive. Does everybody understand how the evaluation of these went? Careful. We find our zeros first, and then we plug in values in between those zeros to find the signs. So I did S prime of 1, S prime of 3, and I could have done S prime of 4. That's a good way of checking. Now we're going to take all of that and we're going to turn it into words. And we're only going to use 3 words: left, right, and stop. Any place where our velocity is negative, we're going to describe that as moving left. Any place where the object is positive, we're going to describe that as moving to the right. And any place where the object, where the velocity is 0, we're going to describe that as the object is stopped. So we say it like this. The object moves forwards, to the right, t is between 0 and 2, and t is greater than 10/3. The object moves backward, t is between 2 and 10/3. Stopped at t equals 2 and 10/3. Now, they also ask an interesting question. And the question is, at what values of t does the particle change direction? And you can see that the values of t for which the particle changes direction are precisely the places where S prime changes sign. And those happen to be at t equals 2 and t equals 10/3 also. So we can say the object changes direction. Any place where S prime changes signs at t equals 2 or t equals 2/3 because S prime changes signs. Does that help? Does that answer your question? Okay, good. Yes. Ah, good question. So there's actually 3 words. Let's do a quick vocabulary. Okay. So position, S of t, be graphed however it's graphed. So from this, we can compute an average velocity delta S over delta t. And that average velocity is always computed over a time interval. It is the slope of a secant line that connects these 2 points. So the full name of the average velocity is the average velocity on the interval t0 to t1. Just like that. Okay? Now, if I let delta t go to 0, then what I get is the instantaneous velocity, or the velocity, which is ds dt, or s prime of t. And that is the slope of a tangent line at time t. So here comes my tangent line, just like that. Notice this is instantaneous because it's the slope at a single point, not over an interval. Now, related to this, but not the same as this, is the concept of speed. And speed is going to be the absolute value of the velocity at that point. At that point. If I needed an average speed, I would do that average speed not with the absolute value of the average velocity, but as total distance over total time. And later, we haven't talked about average speed, but we will in the future. And the reason that this is different is that when I compute average speed, I actually have to count all the downs and all the ups as distance traveled. So I'm not finding the average rate of change here. Instead, I'm adding up in some sense all the backwards plus all the forwards as positive dimension. So this concept, for now, we don't need to worry about. And then finally, we have acceleration, which is spelled S double prime. And then we have some specific words that you need to know. What does moving forward mean?
Positive velocity.
Positive velocity. What does moving backward mean? Negative velocity. And stop.
Zero velocity.
Now, what does speeding up mean? Okay, literally, yes. What do I look for to tell that? No, that's misleading. The slope of the velocity is the acceleration. Uh-oh, you forgot. Speeding up. means I'm moving in a certain direction and I accelerate in that direction. The signs of what?
Acceleration and velocity.
That's right. Velocity and acceleration. Things. And slowing down means that velocity and acceleration have opposites.
Acceleration is
Or v prime. All right. Any other questions? Good. Well, let's take a look at today's main lesson, which is, let me give the big picture. This week we're going to greatly expand your ability to take derivatives. In particular, our goal for today and tomorrow is the derivatives of 6 trig functions. And then after that, we're going to introduce something called the chain rule. It is going to allow you to take the derivative of composite functions or functions of functions. And that's going to greatly expand your vocabulary because you're now going to be able to take different elementary functions that we know and put them together and find the derivatives of those functions. So that's the big picture for the next 4 days, and then we'll apply the chain rule on Friday. Let's take a look now at this question. What I'd like for you to do is to give me a graph of f of x equals sine x, and mark it as well as you can. Yeah. Okay, what does my graph look like? Huh? D? And what sorts of numbers can I put on? What's that?
Can you use numerous parts?
Yeah, sure.
0 over 2, pi,
Okay, where are the zeros?
as 0, pi, and 2 pi.
Uh-huh.
The next one.
Okay. So the zeros are generalized at
Endpoint.
input. All right, well, what about the minimum and maximum values?
Negative 1 pi.
Negative 1 and 1. Okay. And what about the locations of these minimum and maximum values?
2 pi, pi over 2.
Uh-huh.
So, 5 over 2. Negative 2.
All right. Good. Now, here's what I'd like for you to do. You have the graph. I'd like for you to use this graph now to sketch a graph of f prime. Good. Okay, so if we mark up now a number line, so Claire, what was missing from your solution there is you want a good f prime number line. That's how we should start. And we have zeros for our f prime at places where our function has horizontal tangents, and how would we describe those points? Well, I didn't do a very good job of making them evenly spaced, but how would you describe all these zeros? Pi over 2 won't do. I've got a whole bunch of others besides that.
Pi over 2 plus,
Pi over 2 plus n. So 1 plus pi over 2? Plus n pi. Plus 1 pi, plus 2 pi, plus negative 1 pi. Yeah. Or, my other class missed this too. What do you notice about all of the multiples of pi over 2 here? What about those numbers? They're odd. That's right. They're odd multiples of pi over 2. So an easy way to write them, and the way mathematicians usually write them, is 2n plus 1 times pi over 2. This is the way mathematicians say odd. Okay. Now, what about my signs? Positive or negative? Positive. Nice all things. And so putting all that together, looks to me like my slope is about 1-ish right here. So I can make my slope positive but going towards 0, negative but going towards 0. Hey, what function does this look like? It looks like cosine. So this now gives us a conjecture. Maybe f prime of x is equal to cosine x. That would be kind of cool if it were. And it looks like it might be. So to prove that conjecture, we're going to state it first. Our formal, what would be the formal statement of our conjecture? You can put it in if-then form if you like. If what, then what?
if f of x equals sin of x. And f prime of x is cosine.
Yeah. That's it. Good mathematical conjecture right there. Another way of putting that in short is the derivative of sin x is cosine x. So you can state it in either one of these ways. And we're going to prove it, no matter how you state it, by taking the left-hand side here, or the if part, and getting it to look like the right-hand side. Which means we're going to need to find a derivative for sin x, and because we don't already have a derivative rule for sin x, the only choice that we have is the limit definition. We're going to have to take the limit as h goes to 0 of what?
Of x plus h.
Okay, but be concrete. What is our f? So, sine of plus h. Yeah. Remember that the difference quotient is giving us a slope, right? So if I go to a point x, and then I go out to a point x plus h. Yeah. If I did minus, then I would have to have negative h down here as well. Yeah. Okay. Now, I look at this, and here is my big obstacle. I need a way to handle sine of x plus h. And for that, I need to reach way back into my memory and revive the angle addition identity that I have for sine of x plus h. sine of a plus b?
Sine times sine b plus cosine a.
Close. But it's sine and cosine are interchangeable. Should be sine a, cosine b. It's cosine a, sine b. And here, my a is x, and my b is h. So I'm going to write that as the limit as h goes to 0 of sine x cosine h plus cosine x sine h minus sine x, all of that divided by h. Now things got worse here, but they're about to get better. So the first key move, and the important thing to understanding what happened, is that we replaced sine of x plus h with what it is according to the identity. Any questions so far?
What's the if f of x is sine of x?
Then f prime of x equals cosine x.
Then
Then, if, then. Or sometimes you might even see it written like this. Implies. That makes sense? Yeah. All right. Now, I look at this expression and I think, wonder what to do with it, not really sure. So I'm going to start grouping terms. And I'm going to start grouping terms according to terms that have a common factor of sine x and terms that have a common factor of cosine x. Okay. And in particular, I can break this up as sine x cosine h minus sine x all over h. And here I'm using the sum rule for limits. Good basic algebra. But now something wonderful happens. I'm going to factor out that common factor of sine x. In fact, to be clever, I'm going to factor out a factor of negative sine x. Because when I do, then in the top, factoring out negative sine x from this term leaves me with 1. Factoring out negative sine x from this term leaves me with cosine of h. Okay? And in this term, I'm going to factor out the cosine x, leaving me with the limit as h goes to 0 of sine h over h. Notice that sine of x and cosine of x do not depend upon h, so they are constants as far as the constant multiple rule is concerned with respect to h. Now for the payoff. I look at the limits that I have left and I say, hey, look at that. These are two famous limits. What is the limit as h goes to 0 of 1 minus cosine h over h? No! My class had this right away. Come on, guys, make me proud here. Let's try the other one. What's the limit as h goes to 0 of sine h over h? Well, that one's 1. And this one? 0 is 0. So that when the dust settles, what I get is negative sine x times 0 plus cosine x times 1. Simplifies to just plain cosine x. You guys were a little fuzzy on this limit right here. Let's take a minute to remember why. This limit right here is accomplished by the rationalizing, multiplying top and bottom by 1 plus percentage. And on the top here I get 1 minus cosine squared h. But now 1 minus cosine squared is the same as? Sine squared h. And I can write this as sine h over h times sine h over 1 plus cosine h. Fair enough? This limit goes to 1. This limit goes to 0 over 2. And so the whole limit overall is 0. Everybody needs to know how to prove this. And everybody needs to know how to prove the result that the derivative of sine x is cosine x. And that's accomplished with the angle addition identity and our two special limits. Question? So far. Okay. Well, using the same idea, we can come up with a graph of the derivative of cosine. And of course, we need a well-labeled number line, f prime. And now we're going to have zeros here, 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 and here, and signs like so. But now when we graph it, slightly contrary to expectations, watch what happens. We start at 0 here, and we go down. Not sin x. And we end up with a graph that looks like this. What do you figure that is? All right, let's see. Tony's conjecture is that f prime is equal to negative sin x. Let's see if he's right. Set it up for me. The derivative of cosine x should be equal to? Good. Now we need a little bit of angle addition identity for cosine. What is that? If you're not sure, your smartphone knows. Grab your phone.
Cosine x times cosine y minus sine x times sine y.
There we go. So in this case, it would be cosine x.
It's cosine x
Uh-huh.
minus sine x times
All of that minus cosine x. And all of that over h. Good. Okay, where from here?
the first one and the third one
Uh-huh.
is
Good. And this guy is separate. So we get the limit as h goes to 0 of these two terms, cosine x, cosine h, minus cosine x, all over h, minus the limit as h goes to 0 of this term, sine x, sine h, over h. I'm going to be clever and factor out negative cosine x so that we get the form of our famous limit. So, and now the payoff. 0, 1. And negative sine x turns out to be exactly correct. Plus 2 conjectures. That's good. That's a good job. And the time remaining, what I want to do is to show an example. Now, honestly, I've never had occasion to use this particular function for any scientific work, but hey, maybe I could. And in that case, we'd want to know what is its derivative. So we can walk through term at a time, just like we can with our polynomials, and take first of all the derivative of x squared sine x plus the derivative of cosine x plus the derivative of x cubed. And when we get to here, do not forget the product rule. First times the derivative of the second plus the second times the derivative of the first. Notice, just out of habit, I write my trig functions last here, because otherwise it might imply that I'm multiplying the argument. And then for the rest of the terms here, just go term at a time, using the appropriate derivative rule formula.
Can you reenact it?
That's as simple as it gets. So the key is to remember the product. And hey, speaking of product rule, tomorrow we're going to take a look at tangent, cotangent, secant, cosecant. And you can imagine where that's going to go. Let me give you a sneak preview. Not too bad. The derivative of tangent. How could I rewrite tangent so I can make use of my derivatives of sine and cosine? There we go. But then, when I do, guess what I have to use? The quotient rule. So it's low d high less high But now something wonderful happens, because the derivative of sine is times another cosine. And the derivative of cosine is times another negative sine. Positive sine squared x. Do you see what I see? What is it? Cosine squared x plus sine squared x for every single x. Yes! And this whole thing disappears in a poop of smoke. And we usually write the result as secant squared x. We're going to do all that again tomorrow. Sure. Here.